When governments stockpile oil or water, the loudest arguments are usually about who gets to use them. But something interesting emerges when looking past the politics to the raw physical limits of the containers themselves. In The American Prospect, Ryan Cooper looks at the porous sandstone and relentless evaporation at Lake Powell, arguing that physical reality dictates the reservoir should be intentionally drained and abandoned. Meanwhile, Brian Potter details in Construction Physics how the underground salt caverns holding the National Oil Reserve are slowly dissolving and changing shape every time pumps turn on. Placed side by side, these two pieces ask what happens when the natural vaults holding vital resources simply begin to break down. Writing just last week, Ryan Cooper argues that the quickest fix for the Colorado River's water crisis is to drill holes in the bottom of Lake Powell and drain it completely. Notice the specific math he uses to back up this extreme-sounding idea. Because the reservoir sits in a hot, porous canyon, it loses hundreds of billions of gallons to evaporation every year, roughly the same amount of water legally promised to the entire state of New Mexico.
This article was featured in the Daily Prospect newsletter. Sign up for it here. The Colorado River Basin has a problem. It is severely short of water, particularly in its major reservoirs. Both Lake Mead and Lake Powell, the largest and second largest reservoirs in the country respectively, reached record lows this week. Powell in particular is at a level of 3,520 feet, just 30 feet above the intakes for its electrical generators. What is to be done? As I wrote in a previous Prospect print issue, Western water policy is a ludicrous tangle of anachronistic legal precedents and outrageous federal subsidies. Water must be repriced. As my colleague Gabrielle Gurley points out, cattle feed farmers paying $30 an acre-foot, or about 0.009 cents per gallon, while cities pay between $500 and $2,000 per acre-foot, is preposterous. That's half the reason why the shortage has become so bad. Give something extremely valuable away for almost free, and people will waste it. But any such reform will require a massive legal overhaul, and in the meantime, there is a simple and straightforward way to start tackling the problem. Get rid of Lake Powell. Drill some holes in the bottom of that thing and drain her dry. The argument is a simple one. Lake Powell does not directly supply any irrigation system, or any city except Page, Arizona, whose population is just 7,500, and a handful of small Navajo communities. And because it is smack in the middle of a hot, arid desert and built in a porous sandstone canyon, it loses a tremendous amount of water to evaporation and seepage. It is extremely hard to figure out exactly how much is lost. The lake, when full, has something like 2,000 miles of shoreline, but scientists think it's in the ballpark of 800,000 acre-feet per year.
That's about equal to New Mexico's entire legal allotment from the river basin. In short, water is the most important resource in the Southwest, and Lake Powell is losing literally hundreds of billions of gallons of it per year. Now, Lake Mead evaporates even more water than Powell. It is smack in the middle of an even hotter and drier desert. But it does provide water to many farms and cities, particularly Las Vegas. Plans are also afoot to try to cut down on evaporation by such measures as putting up floating solar panels or photovoltaics to shade the lake surface. Initiatives like this would be much more effective if the water were consolidated in one big reservoir, Mead, rather than divided between Mead and Powell. The stated purposes of Powell are to provide water storage, hydroelectric power, and recreation. The first purpose is already irrelevant because the Colorado River is not nearly big enough to fill the existing storage. As Utah State University professor Jack Schmidt points out, the Colorado has more potential storage on it relative to its size than any river system in all of North America, a huge bucket that is mostly empty. Indeed, the combined levels of Powell and Mead are lower than at any point since 1957, that is, before Glen Canyon Dam was even constructed. Powell's vast 25 million acre-feet of theoretical capacity is totally pointless, like some toddler wearing a XXL sweater. The second two purposes are existentially threatened, and almost certainly doomed in the medium term by the water shortage. You can't generate hydroelectricity or go water skiing if there isn't enough water to fill the lake past some minimum.
Already, many recreation facilities on Powell have been either closed indefinitely or moved considerable distances. The river runs right past the old Height boat ramp, which is maybe 10 miles from the lake now. Indeed, it is critically important to start constructing some drain tunnels as a simple safety precaution. If Powell falls by another 30 feet, its power intakes will be sucking wind. If it falls another 120 feet below that, then so will the river outlet works, the only other way to let water out of the dam. This dead pool level is still some distance above the bottom of the dam, and if it is reached, the water running in from the upper Colorado and other tributaries might not be able to overcome evaporative losses for months at a time. In that case, the Grand Canyon would dry up, and there would be no way to get Meade or the lower basin states their legally obligated water. In practice, because of technical problems with the outlet works, the Bureau plans to keep 3,500 feet as the minimum possible pool. Still, a new outlet tunnel at the very bottom of the dam is needed to ensure that Glen Canyon Dam can be bypassed in the pinch. The Bureau of Reclamation does not project that Powell will hit dead pool anytime soon, but it will likely take years to drill any new outlet tunnels. Better to start on it now, or as soon as we get a non-insane president, just in case. It would be unfortunate to lose such a large source of zero-carbon electricity and recreation, but all is not lost here either. The Glen Canyon Dam site is one of the sunniest places in the world. The immense grid connection infrastructure currently being used by Powell's generators, which have a maximum output of 1,320 megawatts, could be adapted to a huge solar battery farm.
As for recreation, the few who traveled through Glen Canyon before the dam went in, like Edward Abbey or Tad Nichols, testified it was one of the most beautiful places on Earth. Most of the reportedly best parts, like the Crossing of the Fathers, Music Temple, the Cathedral in the Desert, Lower Antelope Canyon, and so on, were drowned by the lake. The journalist Zach Podmore has explored the parts of Glen Canyon that have been exposed by the falling lake, some of which have been dry for decades at this point. Much to his surprise, he found that the natural habitat was recovering remarkably fast. It might not make up economically for the end of fishing and boating on the lake, but a restored Glen Canyon would be guaranteed to become a magnet for boaters, hikers, and sightseers from around the world. The current plan from the Bureau of Reclamation is to drain water from upstream reservoirs like Flaming Gorge to protect Powell. The priority should be the opposite, and in any case, none of those reservoirs are large enough to save Powell over the medium term. At some point, the Colorado Basin states and the federal government are going to face facts, whether they like it or not. Editor's note. This article has been updated to clarify Bureau policy regarding the Lake Powell minimum level.
Reading Ryan Cooper leaves a lingering image of Lake Powell not as a political battleground, but as a giant, leaky bucket made of porous sandstone baking in the desert sun. He makes a blunt case that the container itself is fundamentally broken, losing hundreds of billions of gallons to evaporation and seepage. Turn the page to Brian Potter, and the focus shifts from water in a canyon to crude oil underground. Potter looks at the Strategic Petroleum Reserve, which holds hundreds of millions of barrels of oil inside massive salt caverns. What jumps out reading these two together is how they both strip away the intense politics surrounding these resources to look strictly at the physical reality of where they sit. Just as Cooper points out the physical failure of storing water in porous rock, Potter explains the hidden cost of storing oil in salt. Every time oil gets pumped out of the reserve, the caverns degrade and change shape. Read alongside Cooper, Potter's explanation of the oil reserve feels less like a simple engineering lesson and more like a warning about the fragile, temporary nature of these massive storage solutions. Whether it is a canyon losing water to the sky or a salt cave slowly dissolving in the dark, the Earth eventually compromises the container.
The U.S. Strategic Petroleum Reserve, or SPR, is the largest crude oil storage facility in the world. It's capable of storing 714 million barrels of oil, slightly less than 10% of the U.S.'s annual oil consumption. Built in response to OPEC's 1973 oil embargo, the SPR was created to insulate the U.S. from oil supply shocks, to make up for shortfalls and prevent steep price increases should oil imports be imported. In the years since its creation, it has become one of the most frequently used energy policy tools in the U.S.'s arsenal. The SPR has gotten a great deal of attention lately, as the Trump administration has steadily delivered oil, around 120 million barrels as of this writing, in response to Iran closing the Strait of Hormuz. Much of this attention has centered on technical factors related to how much oil can safely be released from the reserve. Various folks have claimed, for instance, that the minimum safe operating level of the SPR is 300 million barrels of oil, a level that it went below the week of August 7. And below that, damage to the storage facility can occur. It's not clear if the specific claim about the 300 million barrel level is true, but due to the way the SPR was constructed, it does indeed have limits on how much oil can be removed from it, and how many times it can be emptied. Given the ongoing importance of the SPR, it's worth understanding how it was built and how it works now. Origins of the Strategic Petroleum Reserve. Almost as soon as oil became strategically important to the U.S., people began floating the idea of stockpiling it for emergencies.
The first strategic stockpiles of petroleum in the U.S. were created for the military. A Naval Petroleum Reserve, or NPR, was created in 1912 by setting aside land containing oil deposits in California, and by the 1920s there were 4 NPR sites across the country. During World War II, Secretary of the Interior Harold Ikes advocated stockpiling petroleum for military and civilian needs, and was appointed president of the Petroleum Reserves Corporation, a government corporation that tried, but failed, to gain control over Middle East oil fields for emergency reserve purposes. In 1952, President Truman's Materials Policy Commission proposed maintaining an emergency oil reserve, and President Eisenhower suggested creating one following the disruption of oil imports during the Suez Crisis. But it wasn't until the 1973 OAPEC oil embargo that the idea for a petroleum reserve for both civilian and government use stuck. By the early 1970s, the U.S.'s demand for petroleum was increasingly outpacing domestic production, making the country more and more dependent upon imports. Between 1963 and 1970, the U.S.'s surplus oil capacity, how much domestic production could be boosted in the event of a crisis, had fallen by 75%, and between 1967 and 1973, U.S. oil imports more than doubled. When OAPEC declared an oil embargo in October 1973, the impact on the U.S. was immediate. Gas prices jumped by over 40%, and widespread gasoline shortages occurred. Even before the embargo, in response to tightening oil supplies and frequent threats from Middle Eastern countries to withhold oil, the Nixon administration commissioned a study on the impact of a major oil supply disruption from the National Petroleum Council.
The Council's report, released a few months before the embargo, suggested that a large petroleum reserve could act as a buffer for import shortfalls. It considered several possibilities for storing the oil, including simply leaving known reserves in the ground and above-ground steel tanks, but concluded that the most cost-effective method would be underground storage in caverns hollowed out from large salt deposits, known as salt domes. A subsequent report by the newly created Federal Energy Administration, formed following the oil embargo, and which later became the Department of Energy, likewise suggested that underground salt dome storage was the most economical way of storing large quantities of petroleum. This suggestion became a reality in 1975, when Gerald Ford signed the Energy Policy and Conservation Act. Among the bill's provisions was a mandate to establish a petroleum reserve of up to 1 billion barrels to diminish the vulnerability of the United States to the effects of a severe energy supply interruption. Construction on the SPR began in 1977. Constructing the SPR. When planning the SPR, several options for storing the petroleum were considered, including using large numbers of idle oil tankers. But ultimately, it was decided that the best option was what the National Petroleum Council and the Federal Energy Administration had both recommended: storing the oil in large underground salt caverns. Salt domes are enormous underground salt structures, potentially miles deep and miles across, formed when geologic forces push underground deposits of rock salt up through the rock above.
They were first discovered in the mid-19th century and began to be surveyed extensively in the early 20th century after oil was discovered near a salt dome at Spindletop in Texas. As the salt pushes up into the rock above, it can create pockets around the dome where oil and gas can accumulate. Because rock salt is largely impermeable to oil or gas,
Hollowed-out caverns within salt domes were a potentially attractive place to store large amounts of crude oil. These caverns can be created by a process known as solution mining, drilling a well down into the salt dome and pumping water into it. The water dissolves the salt, and the resulting salty brine gets pumped back out, leaving behind a void where the salt had been. Mining rock salt by using water to dissolve it had been practiced in Europe for hundreds of years, but modern solution mining, drilling a well into an underground salt deposit and pumping water into it, first began around the 1860s, 1870s in New York. By the 1970s, solution mining had become a widely used method for mining salt. Companies like Morton Salt used solution mining to obtain salt for food products, and Dow Chemical used solution mining as a source of chemical feedstocks. Initially, the underground caverns created by solution mining were simply abandoned, but by the mid-20th century, they had begun to be used for underground storage. In the 1940s, Canada first considered solution-mined caverns for underground storage, and beginning in the 1950s, it had become a popular method of storing liquefied petroleum gas, LPG, in North America and Europe. By 1976, private firms in the U.S. had created over 900 solution-mined caverns, with a total storage capacity of 300 million barrels.
For storing unprecedented amounts of petroleum, solution-mined salt caverns were the obvious choice, and that's what was chosen to create the Strategic Petroleum Reserve. The Texas-Louisiana Gulf Coast was chosen as the location for the reserve. Not only did the area have numerous salt domes that could be utilized for storage, but it was close to existing oil and gas infrastructure, making it easier to fill the reserve and draw it down when required. Construction would be split into 3 phases. In Phase 1, several existing salt caverns would be converted into crude oil storage at 5 sites along the Gulf Coast. 4 caverns at Bryan Mound in Texas, 5 caverns at West Hackberry in Louisiana, 6 caverns at Bayou Choctaw in Louisiana, 3 caverns at sulfur mines in Louisiana. In addition to these solution-mined caverns, the SPR would also use a conventionally mined salt mine at Weeks Island in Louisiana. Collectively, the Phase 1 sites would give the SPR 248 million barrels of capacity, and because the caverns already existed, they could begin to be filled with oil quickly. In Phase 2, 29 new solution-mined caverns would be created at these sites, adding another 290 million barrels of storage capacity. In Phase 3, a new site would be added at Big Hill in Texas, which would bring the total storage capacity to 750 million barrels. Due to political pressure to get oil stored as soon as possible, the construction schedule was compressed, and the first oil entered the SPR in 1977. But the project was soon mired in setbacks. The Federal Energy Administration employees tasked with overseeing the project had little experience in managing large construction projects, and cost control proved difficult. Material and equipment specifications were created before plans were fully complete, creating problems when the selections later proved to be unsuitable. Equipment such as pumps was often chosen because of availability, not because it was best suited for the job, resulting in breakdowns and costly workarounds. Contractors taking advantage of management inexperience engaged in extensive fraud. Used valves were sold as new, and drill bits were purchased, stolen, and then resold back to the government. One contractor was indicted for stealing 18 truckloads of equipment worth $427,000. Another was accused of making off with $8 million worth of petroleum bound for Bayou Choctaw and pumping in hazardous and toxic wastes instead, though the government denied that this occurred. By the late 1970s, over 24 SPR fraud cases were being investigated simultaneously. And while the SPR project was broadly popular, it nevertheless had its share of opponents who tried to slow down the project. The governor of Louisiana, Edwin Edwards, felt the SPR was wasteful government spending and led a virtual one-man crusade against the project, using various environmental protection regulations to slow it down until he was sufficiently convinced that it would benefit Louisiana. Among the concessions Edwards was able to extract were slowing down site conversions to minimize the loss of local jobs and getting the SPR office located in Louisiana instead of the originally planned Houston. There was also broader environmental opposition.
Creating the SPR caverns during phases 2 and 3 would require creating and then disposing of large amounts of brine. While some of this brine could be pumped back underground, the lion's share of it would be disposed of by pumping it into the Gulf of Mexico. But local fishermen, worried about the potential impact on fish and shrimp populations, objected, ultimately forcing brine disposal pipelines to extend much farther into the Gulf of Mexico than originally planned. Securing the necessary environmental permits required an enormous amount of time and effort in the first few years of the program, and by the end of 1978, the SPR office had completed 25 NEPA-required environmental impact statements. There were also numerous technical challenges involved with building the SPR. Phase 1 of construction involved converting existing solution-mined caverns, but these caverns had not been created for the purposes of petroleum storage. Some of them turned out to be unsuitable, others were workable but proved to be incapable of holding as much petroleum as originally projected due to pressure limitations. Collectively, the Phase 1 caverns ultimately had 87 million barrels less storage capacity than first anticipated. Technical challenges continued during Phase 2, when solution mining of the new caverns began. Historically, most solution-mined caverns had been on the order of 1 million barrels in size. A few had reached the 4 million mark, but most of the Phase 2 caverns would be 10 million barrels or more, far larger than previous solution-mined caverns.
SPR officials learned as much as they could about solution mining caverns for petroleum storage from studying the West German Petroleum Reserve, which also used solution-mined caverns and was already in operation. But the much larger scale of the SPR, 700 million barrels versus Germany's 30 million, meant that they were operating in uncharted territory. When mining began, for instance, it was found that brine could be disposed of underground much less quickly than anticipated, and that leaching took far longer than anticipated, both of which slowed down cavern construction. Collectively, the technical, political, and managerial challenges encountered when building the SPR drove up costs and pushed back delivery dates. In 1976, the estimated cost of the SPR through Phase 2 was $766 million. Just 2 years later, that had risen to $1.47 billion, around $7.5 billion in 2026 dollars. The original plan called for Phase 3 to be complete by 1983, with 750 million barrels of crude in the ground. But the actual fill level in 1983 was roughly half that, with many caverns yet to be completed. Between 1980 and 1993, 49 new solution-mined caverns for the SPR were created, bringing its total storage capacity up to 750 million barrels. But the actual fill level would remain at just over 500 million barrels into the 2000s. Since its completion, the SPR has continued to evolve. The small sulfur mine site began decommissioning in 1992, and in 1996, the Weeks Island facility began to be decommissioned when it was realized that groundwater was slowly leaking into it. And over the last 20 years, 3 of the remaining Phase 1 caverns have been decommissioned, bringing the total number of storage caverns down to 60. Operating the SPR. At a high level, the way the SPR works is relatively simple. Each cavern in the SPR is filled up with oil, which sits on top of a heavier layer of brine beneath it. To remove oil from a cavern, water is pumped down into it, which forces oil out the top. To fill the cavern back up with oil, oil is pumped in as brine is pumped out. The caverns are thus always completely full of liquid. The only thing that changes is where the oil-brine boundary is. But this high-level description belies a lot of complexity. We think of physical infrastructure as something relatively static and unchanging, but in the SPR, various forces are constantly reshaping the caverns. One of these forces is cavern creep. The SPR caverns are thousands of feet below ground, and the weight of the ground constantly squeezes the sides of the caverns, compressing and shrinking them over time. As the caverns are squeezed, the liquid inside the caverns is pressurized, and this pressure, in turn, tends to resist further compression of the caverns. But if that pressure is relieved, which occurs during well repair operations known as workovers, cavern creep can accelerate.
The SPR loses up to 2.4 million barrels, about 0.33%, of storage capacity each year due to the effects of cavern creep, depending in part on the number and length of workovers required. In the other direction, removing oil from the caverns requires water to be pumped into them. And when fresh water is pumped into the caverns, it dissolves some of the salt from the walls of the caverns. Every 100 barrels of water pumped in dissolves around 15 barrels of salt. Removing all the oil from an SPR cavern thus increases its size by about 15%. Because of this, SPR caverns have a finite lifespan.
After enough drawdowns, the walls of the cavern become too thin to use it for storage. They can no longer withstand the stresses and may begin to leak oil into surrounding caverns or outside the salt dome itself. Various factors affect how the walls of a cavern wear and how many drawdowns it has available. Phase 2 and 3 caverns, designed specifically to store petroleum, are tall and thin, like skyscraper-sized cigars, and are spaced far enough apart to allow for significant cavern growth over time. But many of the Phase 1 caverns, which were originally mined for other purposes, have irregular shapes or thin cavern walls that make it infeasible to use them for multiple drawdowns. These caverns are thus known as single-cycle drawdown caverns. There are currently 11 Phase 1 caverns in use at the SPR, and 6 caverns that have 1 drawdown or fewer remaining. Cavern lifespan is also affected by how a cavern is used. When a cavern is fully emptied, wear on the cavern walls is relatively uniform. But if the cavern is subject to multiple partial drawdowns, removing a bit of oil, then filling it back up, then removing a bit more, etc., this concentrates wear at the bottom of the cavern, resulting in undesirable shapes that can more rapidly reduce cavern lifespan. Conversely, it's also possible to increase cavern lifespan by strategically emptying caverns in such a way as to wear the cavern into a more desirable shape. Cavern wear is not simply water dissolving the salt and the walls get thinner. The geology of the SPR caverns is complex, and they can wear in complex ways. Changing stresses in the walls can cause salt falls, when a chunk of salt falls into the cavern, or open up cracks and fissures, causing leaks. Because of this, Sandia National Labs closely monitors SPR cavern conditions using tools like sonar. Each year, it puts out a report estimating how many full drawdowns each cavern still has available. Because it can be hard to predict cavern behavior after repeated drawdowns, the maximum number of drawdowns it simulates is 5. Thus, a cavern with 5 available drawdowns today might actually have several more than that available. Limits of the SPR. The limited lifespan of SPR caverns and the complex wearing forces that they're subjected to have led to a lot of speculation and assertion about how much oil can be safely removed from the SPR. Folks often claim, for instance, that the SPR can't go below 300 million barrels of oil without damaging the caverns. I decided to look closely at what these limits actually are. One limit on the SPR is that a minimum amount of roof oil must be kept in the caverns to prevent water at the top of the cavern from dissolving and damaging the cavern ceiling. As of 2016, this was about 12 million barrels, or around 1.7% of total SPR capacity. Another limit you will often see mentioned is 70 million barrels. For instance, the DOE told CNBC earlier this year that 70 million barrels was the minimum amount needed to safely operate the SPR. It's not amazingly clear what's behind this limit, but this may be simply using the DOE's definition of a full drawdown, which is when 90% of the oil in the SPR has been removed. 70 million barrels is about 10% of the SPR's total capacity. It's not clear if there's an actual physical limit at 70 million. That may be the level at which the oil-brine interface would be above the oil intake well, for instance, or if that's simply a defined operational limit. Above these lower limits, you see various claims about operating levels below which damage to the SPR starts to occur. Earlier this year, a J.P. Morgan energy analyst claimed that 150 to 160 million barrels must remain in place to preserve cavern stability and maintain operational flexibility. Rapidan Energy, founded by former George W. Bush energy advisor Bob McNally, claims that this limit is at 170 million. A professor of petroleum engineering at Texas A&M, Siddharth Mishra, claims that the operational limit is between 250 and 300 million barrels, below which the risk of structural damage increases while the system loses its ability to pump oil at high speeds.
Former Biden energy advisor Amos Hochstein claims that he, quote, know plenty of people who think we can't get near 300 because physically you will damage the caverns where the oil is stored. Some of these claims can be verified. For instance, it's true that draining the SPR beyond a particular point reduces the speed at which oil can be pumped out of it. Oil can only be pumped so quickly out of an SPR site, so as caverns empty, the drawdown rate drops. Additionally, because of the aging SPR infrastructure, as well as the downtime needed for repairing that infrastructure, not all the oil in the SPR is available for drawdown at any given point. For instance, a recent GAO report noted that oil at several SPR sites might be unavailable during warmer months due to vapor pressure. Oil stored in the caverns gradually absorbs methane and gradually warms up, both of which increase the vapor pressure within the oil. To be safely distributed, the vapor pressure in the oil must be below a certain level, which can be achieved at a degasification plant.
But several years ago, the SPR's degasification plant was dismantled and hasn't yet been replaced, limiting its ability to distribute crude during warmer times of the year. More generally, the SPR has a huge maintenance backlog and has been described as being held together with Band-Aids. A planned large-scale SPR renovation and maintenance program, Life Extension Phase 2, began in 2021, but was scaled back due to high costs. There have also been various reports noting that the SPR may not have the ability to respond to a severe supply disruption below a level of 250 to 500 million barrels, and that outside of true emergencies, it would be prudent to keep it above this level. However, no official report by the Department of Energy, the GAO, Sandia National Labs, or any other government agency mentions specific fill levels below which damage to the SPR occurs, other than the small amount of roof oil required. While Sandia puts out an annual report on the number of available drawdowns on a cavern-by-cavern basis, it doesn't note any SPR-wide fill level limit below which damage occurs. I similarly wasn't able to find any independent analysis or report pointing to some minimum SPR fill level and explaining specifically what drives it. So it's not particularly clear to me what the source of claims about very high minimum fill levels is, if it's from people talking to Sandia DOE folks in some unofficial capacity, or if they're inferring limits based on cavern stress data that Sandia provides but doesn't make explicit, or something else. It's notable to me that claims about minimum fill levels aren't particularly consistent, and that different analysts or experts give widely different limits. It's also notable that these claims often conflate different limits.
The Strategic Petroleum Reserve is the largest petroleum storage facility in the world and stores vast amounts of crude oil, over 700 million barrels, in underground salt caverns. These caverns behave in complex ways. They grow, shrink, and distort over time due to the various fluid and geologic forces that they're subjected to, and the caverns have a limited lifespan due to water gradually dissolving the solid salt walls. Because of these complex forces and the gradual damage that gradually accumulates across the walls of the caverns, there's widespread speculation and assertion that the SPR can't be drained below some particular level without inflicting serious damage on the underground caverns. It's hard to know how seriously to take these claims. Many of them are made by experts, such as professors of petroleum engineering and former White House energy advisors. And there are various limits associated with removing oil from the SPR, such as the oil needed to keep water from damaging the roof of the caverns or the drop in withdrawal rates that occurs as the SPR empties. But it's hard to find any sort of actual published estimate of these limits in a report or official document. This doesn't mean that these claims are wrong, but it does make me wonder where the claims are coming from. The Naval Petroleum Reserve later became part of a major presidential scandal during the Harding administration, when Secretary of the Interior Albert Fall accepted bribes to let companies lease NPR lands at Teapot Dome in Wyoming. Extracting pre-existing brine deposits dates even earlier, to China, around 250 BC.
The SPR also has a statutory storage limit of 252.4 million barrels, but this only applies to a particular type of release, one that, as far as I know, has never actually been conducted, so in practice, this is a meaningless limit.
A concrete dam wedged into a desert canyon and a hollowed-out salt dome share the same quiet flaw. The Earth is never just a passive bucket. Sandstone drinks water, and salt slowly buckles under pressure. What lingers from these stories is a sense of physical friction. Modern life relies on massive systems, built on the assumption that the ground will simply sit still and hold whatever gets poured inside. But geology always pushes back. When the rock beneath the surface refuses to cooperate, what gives way first, the engineering or the expectation?